We've got all of our theory done with some small examples in the middle. Let's start to put it together with some bigger picture examples now where we combine some multiple thoughts together. A capacitor, remember that a capacitor is just two plates. Each one of them is charged. One is positive, the other is negative. Capacitor is charged to a potential difference of 12 volts. So right off the bat, first bit of information is delta V equals 12 volts. We might also remember here that the negative plate is the one at low potential and the high plate is the one at, the positive plate is the one at high potential. The distance between the, I said places, that should be plates. The distance between the plates is 2 millimeters. We can put that on our picture if we wish. 2.00 millimeters, we can write it in meters if we wish, 2 times 10 to the minus 3 meters. Okay, so there's our setup. We know our potential difference and we know the separation between the plates. Which plate has high potential and which plate has low potential? So we kind of said that when we were putting our initial thoughts together. What we know is that electric field, E, points toward low potential. We also know that E is out of positive and in towards negative. So we can put those two things together. We see that our electric field points towards the right. That's because it comes out of the positive and into the negative. And we know that since it points towards lower potential, our negative plate must be low potential and our positive plate must be high potential. One thing that's kind of interesting here, you don't actually know what is the potential at the negative plate, and you don't actually know what it is at the positive plate. All you know is the difference between them. That's sort of an interesting thing to think about. Just like when we talk about gravitational potential energy, you say that U is equal to m times g times h. But that choice of h is a little bit funny. Whatever h is depends on wherever you call ground, and you can call a lot of different things ground. So you could call the top of your table h equals 0, or you could call your floor h equals 0. So potential energies, really the thing that matters is the change, right? So as you go over a distance, how does it change? That's true for potential as well. It's the change that's always really important. So you don't, the one specific number is not that important. What it is compared to another is more important. Okay, that's a little bit of rambling, but hopefully it gave you a little bit of context. Part B, find the electric field between the plates. So we know that electric field is a vector. It has magnitude and direction. When we look at our picture, we can see that E points right. That means we've got the direction sorted out. Now let's find the magnitude. The size of our electric field is the size of our change in potential divided by our change in distance. So if we take 1 point at the high plate, 1 point at the low plate, we know that delta X is 2 millimeters, and we know that delta V between those two plates is 12 volts. So we have 2 points that we're going to talk about. So our delta V between those 2 points is 12 volts. Our delta X between those 2 points is 2 millimeters, or 2 times 10 to the minus 3 meters. That gives us the size of our electric field is 6,000 volts per meter. And our electric field vector then is 6,000 volts per meter in the X direction. Okay, the next part, what is the electric potential exactly in between the two plates? This slide is a bit full, so we'll go on to the next one. To think about the electric field in the middle of the two plates, let's kind of get some coordinate systems on here. So I'm going to call my distance at the negative plate S equals 0. My distance in between the two plates, that would be S equals 1 millimeter. Then of course my distance at the positive plate would be S equals 2 times 10 to the minus 3 meters. I know that my S equals 0 plate, so at my S equals 0 plate, so my potential at the negative plate is equal to my electric field times my value of S, so 6,000 volts per meter times S, which is 0, equals 0. So my potential at the negative plate, because I pick S equals 0 at the negative plate, is 0. Let's find my potential in the middle. So what is my potential here along this middle line? My potential at the middle, I'll just write M for middle here, is equal to E times S, 6,000 volts per meter, times my distance of 1 times 10 to the minus 3 meters, gives me a potential in the middle of 6 volts. This makes sense logistically. The potential between the two plates overall is 12 volts, so the potential at the middle should be half that at 6 volts. So C makes sense. We'll go on and do part D on the next slide. This example finishes up then with part D. What would be the change in potential energy, electric potential energy, of a proton moving from the positive plate towards the negative plate, as far as the negative plate? So for this part, we're going to have to remember that the charge on a proton is equal to plus the fundamental charge, so plus 1.6 times 10 to the minus 19 coulombs. We know that our plates have a high potential at the positive plate, a low potential at the negative plate, and our proton is going to start right here at our positive plate. That's our initial point. It's going to move all the way over to our final plate, to the negative plate. That's where it's going to finish. That's the final point. So let's make sure we remember we're doing the proton. Our expression for change in electric potential energy, delta U, is equal to the charge times the change in potential. And that's our expression for potential energy, or change in potential energy. The charge that we have is the charge of a proton. Our change in potential energy is V final minus V initial. And let's see what we know we can put in here. Charge of the proton is 1.6 times 10 to the minus 19 coulombs. V final is at the negative plate. On the previous slide, we showed that since we decided S was equal to 0 at the negative plate, the potential at the negative plate was 0. Minus our V initial, so since the potential difference is 12 volts, if the negative plate is at 0 volts, the high plate must be at 12 volts. Put that through the calculator and we get a change in electric potential energy of minus 1.9 to times 10 to the minus 18 joules. Really important to stop and take stock of your answer. The proton is a positive charge. When released from rest, it will move on its own towards the negative plate, and it will move towards lower potential energy. So it makes sense that the potential energy gets smaller. Okay, what about an electron? What if it starts at the positive plate and moves to the negative plate? So exactly the same motion in the same area, but a different charge. Let's see what happens here. So when we're talking electron, same equation, delta U equals the charge times delta V. The charge we're talking about is the charge of an electron. Charge on an electron is minus the fundamental charge, because electrons are negative. And delta V is V final minus V initial. So that's minus 1.6 times 10 to the minus 19 coulombs times V final, which is 0, minus V initial, which is 12 volts, gives us a change in electric potential energy of positive 1.92 times 10 to the minus 18 joules. And if you were thinking about what that meant, we see that our electron has an increase in potential energy. The only way to get an increase in potential energy is to do work on something. So that electron would have had to be pushed to the other side. It wouldn't have done that by itself. Just like if you want the gravitational potential energy of a car to increase, you have to push it up the hill. It won't go on its own. Let's do another electric potential energy example. So we're given that a uniform electric field with a magnitude of 6,860 newtons per coulomb points in the positive x direction. So we'll put in 2 plates. Let's draw in our electric field. And let's write down our electric field vector. E equals 6,860 newtons per coulomb in the x direction, so we'll put in an x hat. Let's put in our coordinate system, x and y. I would say right off the bat, why don't we put in some stuff that we know before we even keep reading? Electric field points from positive to negative, so the left plate must be negative or positive, and the right plate must be negative. Electric field points from high potential to low potential. Let's label that in there too. Okay, now we kind of have a picture of what's happening. Part A, find the change in electric potential energy when a positive 19.5 microcoulomb charge is moved 4.25 centimeters in the positive x direction. So let's get a picture of that. So for part A, I'm going to take a positive charge and we're going to move it 4.25 centimeters to the right. Then we're going to find what happens to the electric potential energy. You might want to ask before we even begin any calculations, does the electric potential energy get bigger or smaller? That's a good thing to have in your mind before we even get started. Okay, next thing we can do is let's write down, and we've got to do this sort of thing again in B and C. Why don't we write down the equation for electric potential energy? So electric potential energy is charge times potential. So change in electric potential, delta U, is Q times delta V. Delta V, remember, we can find from knowing our electric field because the x component of our electric field is minus delta V over delta x. So our change in electric potential energy is going to be Q times minus EX times delta X. Then I'll drop the brackets and haul my minus sign out front. Minus Q EX delta X. So let's see what we've got going on here for part A. Our change in electric potential energy is minus Q, 19.5, times 10 to the minus 6, because micro, mu, means minus 6, times EX, that's the x component of the electric field, 6860 newtons per coulomb, times delta x, it moves 4.25 centimeters to the right, 0.0425 meters. Gives us a change in electric potential energy of minus 0.00569 joules. You could write that as minus 5.69 times 10 to the minus 3 joules, or minus 5.69 millijoules. Either is fine. Okay, let's do part B next. What's happening in part B? In part B, we have the same charge, but it's moved 4.25 centimeters to the left. Oh, I'm sorry, I just realized I asked you to think about something and then I didn't circle back around to it. For part A, I said, should we expect the potential energy to be bigger or smaller? Well, if our positive charge is moving with the electric field, that means it would move that way on its own. That means it moved towards lower potential energy. And we know that the energy depends on the potential. It moves towards low potential, so lower potential energy. Okay, part B, we're taking the same charge and we're moving it to the left. So right off the bat, you might notice that your delta x becomes negative because it moved left. We probably also anticipate that our potential energy is going to get bigger because we're going closer to a high potential. Okay, let's get going on our equation. Delta U is equal to minus our charge, 19.5 times 10 to the minus 6 coulombs, times our x component of the electric field, times our delta x minus 0.425 meters. That minus came in because it moved left. That gives us a change in electric potential energy of plus 0.00569 joules. Okay, same size as above, but different sign. So the potential energy gets bigger because we're moving closer to the positive plate. We're storing extra energy. Part C, find the change in electric potential energy when our positive charge is moved 4.2 centimeters in the positive y direction, or moved up. So we're going this way. We've got a delta y equals 4.25 centimeters, and our delta x is actually equal to 0. It doesn't move left or right. Okay, let's use our equation. Delta U is minus our charge times our electric field times our delta x. Well, it doesn't move left or right, so delta x is 0. No change in electric potential energy. That's not surprising because there's no change in potential, and potential energy depends on potential.